All right, we looked at graphing polynomials. We've looked at simplifying and dividing uh, rational expressions in chapter 1 and chapter 2. Now we're looking at dividing polynomials. We break this into 2 to 3 videos. Some of the problems can get lengthy. I'm sure you're excited. So section 5.2, we're going to start with something that looks complicated but isn't so bad. This looks crazy. Don't let all the letters and the numbers and all the superscripts and subscripts confuse you. All this says is if we have a series of x's, x to the 2, x to the 1, x to the 3, x to the 4, x to the 5, x to the anything, and those x's or y's, whatever, have a number in front of them, then we have what's called a polynomial. So this is just what a polynomial is. And I'm going to give you some examples that should look a lot less scary. Here's a polynomial. It has an x to the second power, has an x to the first power, it has really an x to the 0 power, because anything to the 0 is 1. So it goes 2, 1, 0. That's it. That's all this definition says, is this is a polynomial, where each non-negative integer we have for some coefficient. If the number before x was 0, then it just wouldn't really be there. And so that we have our polynomial, or a polynomial function here. It talks in this definition here about the degree. The degree n is whatever the biggest exponent is, and then going on down. So this would be a degree 2. This is a polynomial of degree 2. This is another polynomial. We've got 3x plus 4. The highest exponent here is 1, x to the 1 power, and so this would be a polynomial of degree 1. We have another one here. You'll notice that this doesn't quite go down in order. It doesn't go 5, 4. We're missing the 4. We don't include it, but there would be like a 6, x to the 5th plus 0, x to the 4th. So when it's all written out, you wouldn't show it, because a sub n, that whatever it is not 0. X to the 3rd, there's no x squared, so we're going to have like a plus 0x squared plus 3x plus 0. So it kind of skips around a little bit, but it's still a polynomial function, because we have x's with exponents, we have coefficients in front of them. So it would be a 5th degree polynomial, even though there's only 3 terms. So this would be 3 different terms, a trinomial. We have a 5th degree polynomial. That's how you talk about the degree, and that's just what a polynomial looks like. So that's what that definition says. Dividing polynomials. What we have here is we have a 3rd degree polynomial in the numerator and a monomial, basically a trinomial on top, and we have a polynomial of degree 1 in the denominator, and there's only one thing here, so this is a monomial. This is probably the easiest type of division that we can do. That being said, I'm going to write it in a complicated way at first, because I do want to express the underlying math of what you're doing, and then I'll also talk about the shortcut. I'll talk about the way that to get the answer quickly without doing all the extra steps in between. So I'm gonna show some steps here that I won't show anymore after this, because I want to make sure I talk about the underlying math as well as the shortcuts and what we would practically do when doing these problems. So what this says, or one way I can address this problem, or I can attack this problem, is I can view it in a slightly different way. I can basically look at this as, or factor out 1 over 2x from each of these terms. So if I distributed this back through, they would all have a common denominator of 2x. I can factor that out. And so this is a different way of viewing it. And while it seems like what's the point, this is what's really kind of going on, is we have this numerator multiplied by 1 over 2x. If I do distribute that through, so I'm kind of breaking up the fraction, I would get this. If I distribute that to 1 over 2x through, I get this. And again, it seems like extra steps because it kind of is. But again, this is what's going on behind the scenes. Now that we've broken this original fraction up into 3 different fractions, common denominators here, so it all works out, we can view them as really 3 separate problems. We've got 2x cubed divided by 2x, 10x squared divided by 2x, and 6x divided by 2x. If I work from the right to the left, 6x divided by 2x, 6 divided by 2 is 3, x divided by x is 1, so this would just be 3. 10x squared divided by 2x, 10 divided by 2 is 5, and remember that when you're dividing with exponents, with these powers, you can subtract the exponents. So 2 minus 1 would be just x to the 1. You could also think about it as this is x times x divided by x, so one of those x's divides to 1 or cancels away. So we'd end up with 5x here, minus 5x, and 2 divided by 2 is 2. X cubed divided by x would be x squared. So this would be my result. If I were going to do this problem myself, what I would probably do is I would view this as 3 different problems. And I would say 2x cubed divided by 2x, x squared, 10x squared divided by 2x, x to the 5th, 6x divided by 2x is 3. This shortcut only works if you have a monomial in the bottom. There's no adding or subtracting in the bottom. So I do want to emphasize that this only works because there's a common factor in the numerator here of 2x that you could factor out. And so that's why it works. So be careful with taking this shortcut if there's a plus or a minus on the bottom. It doesn't always work that way. Let's look at another example here. So again, I'm going to view this as 2 separate problems. I'm going to do 30x cubed y fifth divided by x squared y to the second. And I'm going to do 25xy divided by 5x squared y to the second. So here are the 2 ways that I'm kind of viewing this problem. Because there's a monomial in the denominator, there's no adding or subtracting, so you don't have to worry about that. So if I look at this first one, on the left here, I've got 30 divided by 5 is 6, x cubed divided by x squared is x, y to the 5th divided by y squared, 5 minus 2 is going to give me y to the 3rd. Looking over here, 25 divided by 5 is 5. Now this is a little different. If I use my exponent rules, this would be like 1, an exponent of 1 minus 2. So I'd have x to the negative 1, and an exponent of 1 on the y minus 2, and have a y to the negative 1. However, if you recall, we don't like to have negative exponents because it doesn't really make sense in our way of addressing exponents. You know, y cubed is y times y times y. What is x to the negative 1? How can you multiply x times itself negative 1 times? And so the way we address, or the way we deal with these negative exponents is we turn into a fraction. And so that negative 1 just means it stays in the denominator. The negative 1 here means it stays in the denominator. So we'd have 5 over xy. Remember that if you look back at this fraction here, 25 divided by 5 is a positive 5. And so that 5, it works out to be just 5. So that 5 stays on top. You could look at it as I have 1x in the numerator and 2 x's in the denominator. So when I cancel those x's away, 1x would stay in the denominator. And that's another way of looking at this situation to get the 5 over xy. So that's how you divide with polynomials if there's a monomial in the denominator. If there's a adding or subtracting in the denominator, we're dividing one polynomial divided by another polynomial where it's not a single monomial in the denominator. Now we have to do it in a different way. So there are 2 methods that we can use. There's long division, and there's something called synthetic division. Long division, you may have scoffed at this when you were in 5th grade, 6th grade, 4th grade, and said, I'll never need to do this again. I've got a calculator in my pocket. Now you got to do it again. So let's move over. I'm going to move over to the document camera. I'm going to remind you of how to do long division. If you remember how to do long division, you can maybe skip ahead a little bit. If you went, I hate long division, how do I do this? I'm going to walk you through it because as you can see here, we're going to do some long division with polynomials. It's so much fun. I like it actually. So 42, if we're dividing 6,049 divided by 42. The question we're asking is how many 42s go into 6,049? That's the overarching question. The way long division, this algorithm is set up, is we do how many times does 42 go into 6? And there are 0 6s and 4, or 0 42s and 6. So then we ask, okay, what could I multiply 42 by to get close to 60? Well, if I multiply 42 times 1, I'm going to get pretty close to 60 without going over. Kind of like, what was that? Now let's make a deal. Price is right. Can't go over. So 1 times 42 is 42. And I'm going to find the difference. I'm going to see what's left over. So I should get 18 left over there. And I'm going to bring this 4 down. That's how this algorithm works. So now I'm asking, something times 42 is going to give me close to 184. And you can use a calculator. You can work at it however you want. But you're going to end up that if you do 4 times 42, you're going to get 168. And that's pretty close to 184 without going over. And then if we subtract, we're going to get that there's a difference of 16. So I've got a remainder, or I've got 16 left over. Bring that 9 down. And I've already got close to this before. I had 168 before. So when I ask something times 42 gets me close to 169, I know 4 times 162 is going to get me close. Sorry, 4 times 42 can get me close. I've got a remainder of 1. Now this is where you either wrote, depending on what level of elementary school you were in, you wrote an R1 instead of remainder, or you wrote it as a fraction. What this says is we have 1 out of 42 left over. So 1 out of 42. So the answer is that 42 goes into 6,049, 144 times, and 1/42 left over. This is how we typically write a mixed number like that. There is another way of writing a mixed number. And it seems kind of ridiculous, or not ridiculous, but not necessary with numbers like this, with a mixed number. But you could write it as 144 and, or plus 1/42, because that's really what it is. It's 144 wholes plus 1/42 extra. So that's what this is really saying, is plus 1/42. And we're going to use this notation when we start looking at these polynomial functions up here. Okay, so before I come to this problem here, I'm going to go back to my lesson quickly and mention one thing, that if you see this as your problem and you're going to use long division, some of the problems will ask you to use long division specifically, so you do have to be able to do long division with polynomials. It's always going to be the numerator is inside the garage or inside the box, or however you want to view this. It's inside of this notation, and the denominator goes outside. So it should look like this. And I wanted to talk about that specifically because if you flip these around, you're going to get a very different answer. So when you're using long division, the way this algorithm works is you take the numerator and put it inside of this box, and you put the denominator outside. So we're asking how many x plus 2's go into the numerator? How many x plus 2's go into this? Okay, back over to the document camera. Let's see how to do the same process, the exact same algorithm, but with polynomials. So I'm asking, instead of asking what would I have to multiply 42 by to get close to 60, I'm asking what would I have to multiply x by to get to x squared. You'll notice I kind of ignored the 2 for a minute. Going back over here, really when I was looking at the 60, I wasn't concentrating on the 2. I knew that 1 times 40. This could have been a 3. It still would have been 1, because I know that 2 times 40 would give me 80, and that'd be too big. So I wasn't really looking at this 2. This 42 was kind of like an x and 2. So it'd be almost like this was a 40. 40 plus 2 is 42. I don't really care about the 2. I'm really concentrating on that 40. Same thing down here. When I was looking at something times 42 gives me 184, or close to 184, I wasn't really looking at the 4. I knew that 4 times 4 was 16, and that would give me pretty close to 18. So I wasn't concentrating on that ones place. We're going to do the same thing here. We're not going to concentrate so much on this plus 2. We're really going to concentrate on this x. So I know that x times x will give me x squared. And x plus 2 then, because I'm distributing, x times 2 will give me 2x. Just like here, 4 times 4 is 16, 4 times 2 is 8. So I'm distributing here as well, 4 times 10s, 4 times 1s, and I'm getting that. And I'm going to subtract. I'm going to subtract the whole thing. I am putting those parentheses there on purpose. You don't have to put them there, but you need to remember that they are there. And here's why. I'm doing x squared minus x squared, so I'm subtracting just like I did over here, which is 0. But then I'm doing 3x minus a positive 2x. I'm not doing 3x plus 2x. I'm doing 3x minus a positive 2x, which is just going to give me x, or 1x. Now I'm going to pull that 3 down, just like I pulled down the next value over here. And now I'm asking, something times x is going to give me close to x. Well, 1 times x will give me close to x. That'll give me exactly x. 1 times 2 will give me 2. And again, I'm going to subtract. I'm going to find the difference. The difference between x plus 3 and x plus 2 should be 1. Well, let's see, x minus x is nothing. 3 minus a positive 2 is 1. So I have a remainder. I have a remainder of 1. And sorry, this was a positive 1 that I multiplied by. A remainder of 1. So I'm going to write it like a fraction, kind of like here I had 1/42. Write this as 1 x plus 2th, x plus 2, 1 over x plus 2. And this notation down here now becomes a little more relevant. The 144 plus 1/42 plus the remainder of 1/42. We're going to have x plus 1 plus 1 over x plus 2. And that is the final answer. So the correct answer is going to be x plus 1 plus 1 over x plus 2. That 1 over x plus 2, remember, was the remainder. So x plus 2 goes into this polynomial x plus 1 times, plus a remainder of 1 over x plus 2. Not so bad, right? Some of you are rolling your eyes. Let's try another one. Let's move over here to this one. This one looks longer, but I think we can handle it. Move over to my document camera again. Here we are. All right, here we go. Stretch. It's a bigger problem. I think we can do it. Here we are. I want to know something times 3x squared is going to give me close to 3x cubed. Again, I'm going to ignore this for now. If I do x times x squared, I'm going to get the x cubed I want. And I've already got a 3 here. So if I just do x times x squared, I'll get the x cubed, and x times 3x squared, 3x cubed. Okay, so these are exactly the same. That's good. X times plus 5x would be plus 5x squared. X times minus 4, minus 4x. And now I'm going to subtract. 3x cubed minus 3x cubed is 0. That's good. 2x squared minus a positive 5. So 2 minus a positive 5, negative 3x squared. Negative 9 minus a negative 4. So remember, when you're subtracting negatives, it's like adding. You could also think about it as I have 9 negatives, and I'm taking away 4 negatives. I'll end up with 5 negatives. Okay, so I've subtracted. I'm going to pull down the remainder, minus 4. Now I'm asking, something times 3x squared is going to give me a negative 3x squared. Well, if I just did 1 times 3x squared would give me 3x squared, which is not quite negative 3x squared. So I'm going to have to do a negative 1 or a minus 1. So minus 1 or negative 1 times 3x squared gives me a negative 3x squared. Negative 1 or minus 1 times positive 5 gives me a negative 5x, so 5x there. And negative 1 times a negative 4 is going to give me a positive 4. And now if I subtract negative 3x squared minus a negative 3x squared, anything minus itself is going to give me 0. Negative 5x minus negative 5x, again, anything minus itself is going to give me 0. So the x's are all cleared up. And negative 4 minus a positive 4 is going to give me a negative 8. Again, a negative minus a positive, not the same as a negative minus a negative. So we got negative 8. So we have a remainder of minus 8 or negative 8. So I'm going to put minus 8 out of whatever this was. So 8 out of 3x squared plus 5x minus 4. And that would be my remainder. I know it's kind of tiny in there, but it's basically rewriting this original statement right there. So that would be the final answer, x minus 1 minus 8 out of 3x squared plus 5x minus 4. And that's how our division, or the long division method for solving these division problems works. I'm going to stop it, and we're going to look at synthetic division in a separate video.